Boa tarde a todos. Vamos começar, que a gente tem 3 plenárias em seguidas, uma seguida da outra. É um prazer recebê-los para a primeira plenária que a gente tem no colóquio. A primeira plenária vai ser apresentada pelo professor Peter Guttorp. O Peter, além de ser um grande amigo, é um dos melhores estatísticos que eu conheço da atualidade, que trabalha com diversos problemas, trabalha em diversas áreas, mas principalmente na área aplicada. Ele é um professor emérito de estatística na Universidade de Wisconsin, Washington, em Seattle. Um professor da Norwegian Computing Center. Ele é co-diretor da Statmus, que é o Research Network on Statistical Methods for Atmospheric and Ocean Science. É um professor adjunto de estatística da Simon Fraser University. E ele tem uma história bem legal que eu queria contar para vocês. Que primeiro ele tem formado em jornalismo pela Universidade de Estocolmo. Depois ele tem um bacharelado em matemática, estatística, matemática e musicologia na Universidade de Lund. E depois um PhD em estatística em Berkeley, em 1980. Ele trabalha principalmente em modelos estocásticos em hidrologia, ciência atmosférica, geofísica, ciência de meio ambiente e hematologia. Ele é um fellow da American Statistical Association, do Institute for Mathematical Statistics, é um membro eleito do International Statistical Institute e, atualmente, ele é o vice-presidente do International Statistical Institute do quadriênio de 2017-2021. Então, é um prazer ter aqui para falar para a gente. E ele vai falar sobre ciência, história e processos estocásticos. Welcome, Peter.
Thank you very much, both for the invitation and the introduction, which I basically followed. My Portuguese isn't what it should be, even though I'm here for probably about the 10th time. Never been here for very long, that has been the problem. So today I'm going to talk about history of stochastic processes, and my thesis is that the history of stochastic processes is driven by scientific problems, and almost all processes that we normally use originated in a particular problem. Not all, as we'll see as we go along. So I'm going to start by talking about the Poisson process. The Poisson process has nothing to do with Poisson, but I'll show you a nice picture of him a little later. Continuous time Markov chains comes next because they follow logically from the presentation in some sense. I'm going to talk about point processes that are based on Poisson processes. I won't quite get to the work that Nancy and I are doing together, but some of the background to that will come up. I'll talk about discrete-time Markov chains, which were not invented by Markov. This is another example of Steve Stigler's law of epinomy that basically says that no named theorem was invented by the person who named the theorem, and that includes Stigler's law of epinomy. And then we're going to talk about Brownian motion. And Brown actually was the first to see Brownian motion. I'll show you some Brownian motions. And we'll talk a little bit about the theory of it that has a somewhat convoluted history. Okay, so let's start with the Poisson process. I'm going to just make sure that my thing is working. Yep. So the first use of a Poisson process goes way back. if you read Queen's College is a college in Cambridge, and if you read the fellows list of Queen's College, one entry is a guy named John Mitchell. He was a Master of Arts, a Bachelor of Divinity, Fellow of the Royal Society, taxer, which I think means he ran the bookkeeping of the college, professor of geology, lecturer in Hebrew, arithmetic, geometry, and Greek. People did a lot of things those days. But he's famous as an astronomer. He discovered the inverse square law of magnetic action. So that's pure physics. That wasn't on that list either. And he was the first person to describe a black hole. So he, of course, had not observed one. He just realized that they ought to exist because of gravitation. And we'll get back to gravitation. He lived 1724 to 1793, and I've spent lots of time trying to find a picture of him, including sending one of my best friends who happened to be in Cambridge to the college library and hound the college librarian to dig up a picture, but they don't have one. I did find a description of him, though. John Mitchell is a little short man of a black complexion and fat. So that's all we know. Now, the paper we're going to talk about was published in 1767, and you see little red dots show up here and there. That's just to keep track of where we are in time. So this red dot will stay on the Poisson process for reasons that will become clear. Now, 1767 was 3 years after a paper called An Essay Towards Solving a Problem in the Doctrine of Chances was read to the Royal Society. Some of you may know that that was written but not read by Thomas Bayes, and it was published after his death. Whether that influenced Mitchell to start thinking about probability is not clear to me, but it would not be unlikely. This paper comes 3 years later and is called, I always have to look it up, An Inquiry into the Probable Parallax and Magnitude of the Fixed Stars. So let's see what it's about. The Pleiades is a group of stars that is easily visible in the northern hemisphere. By the naked eye, you can see at least 5 of them. People with sharp eyes can see 7. So we're going to look at distances between these. Oops, wrong way. So here's, for example, Maya, one of the brighter ones. And we're now looking at the distance between Maya and Taygeta. And we can do that kind of circle for each of the stars. And then we think of it as a spatial angle, so a 3-dimensional angle. And then we can figure out disjoint sets that would contain the stars. Now, Mitchell's argument was that if there is gravitation, we ought to see clusters. If stars are gravitationally attracted, they ought to group together. More than would be predicted by chance. And predicted by chance is what comes up a lot when you look at the origin of Poisson processes. What people mean by that is conditionally uniformly distributed. which is one way of characterizing the Poisson process under some regularity conditions, which I'm just going to wave my hands about. But if you really want to go look it up in Rennie's book on Poisson processes. So there's about 1,500 stars equal in brightness to the 6 Pleiades. That, according to Mitchell, that's what he could see. The distances of the other Pleiades from Maya are these numbers, 11 through 49 arc minutes. So an arc minute is a measure of area in this case. And if stars are scattered randomly, the question he asked is, what is the probability of having 6 out of 1,500 this close? Well, that's a question that people in probability theory can think of how to answer and have. But he was the first to think about that question, at least in the literature. So he multiplies together the probabilities of at least 1 point within these circles for each of the other stars. And he gets a chance of 1 in 496,000. Now that's wrong. It's wrong because the different circles, of course, are not disjoint. They're included in each other, so they're concentric. So you need to look at the annulus instead of the whole set. But you can do that calculation quite easily. And when you do it correctly, you get 1 in 14 million, roughly speaking. Regardless of which number, this is not very likely. This is a small probability. Oop. That was not what I wanted. We try that. So gravitation is one possible explanation of why things were closer together than pure chance would want. Other people have used similar arguments to prove that God exists. Now, other people have done this calculation. Simon Newcomb, who was the astronomer general in the U.S., a Canadian astronomer, he did a similar computation in 1860, pointing out that Mitchell had got it wrong, and doing it by multiplying together Poisson, by calculating the Poisson probability of getting 6 in the largest of these circles. Which is another way of doing the same thing, getting 6 or more. Poya did a similar calculation in 1919. I'm pretty sure he didn't have a clue that anybody else had done it. It was not with a particular example. It was just the type of problem that he liked to do. So these were all the astronomy ideas. There's been other people who have invented the same type of process. Now, something that's going to come back a couple of times in this talk, if I get far enough, is the kinetic theory of heat. The kinetic theory of heat just says that heat comes from moving molecules bouncing together, very roughly speaking. That was not the dominant theory in the mid-1800s. They thought that heat was a substance called caloric that permeated matter in different degrees depending on how warm it was. And so that could explain a whole lot of things. For example, why things cool down, why water gets colder when you put ice in it. There's exchange of caloric between the water and the ice. The kinetic theory of heat was something really weird that some physicists who believe in atoms had come up with. And nobody believed in atoms except these few stupid physicists who, yeah, you know how things are. They come up with all sorts of weird things, and you can't even observe it, and people were very upset about this whole thing. Anyway, so one of the objections that came up to the kinetic theory was, suppose you go into a room, and somebody lights a cigarette in the back of the room. Now, if the kinetic theory of heat is correct, then you should smell that immediately down here. Of course, you don't. It takes a while for it to get there. But if it could move in a straight line at a high speed, you should smell it almost instantaneously. So Clausius, in 1858, was one of the proponents of the kinetic theory of heat. And so he calculates the distribution of distance between collisions. That distribution is large. That is, if we expect very long distances, then the objection is correct, and we should smell the smoke as soon as somebody lights a cigarette in the other corner. But he gets, of course, a different answer. And in essence, what he does, he computes the probability of no Poisson events in a set. The zero probability of a Poisson process, and therefore the distance to the first event. Everybody who's done elementary probability knows how to go between those two things. Clausius, of course, didn't. He had to come up with it. Here's Clausius. The answer he got was that it's very short, provided there are a lot of molecules in the room. And of course, nobody knew how many molecules there would be in a room. And we'll get back to that later as well. But it seemed reasonable that there wouldn't be a few, there would be a lot. And then the distance would be very small. And so the path that a molecule would take would be diverted over and over, and so it wouldn't go in a straight line for very long. Here's Poisson. I promised you a picture of Poisson. I just think it's a nice picture of Poisson, but he has nothing to do with the Poisson process. He invented the Poisson distribution as an approximation to the negative binomial, which was difficult to compute. The negative binomial was difficult to compute. And he wasn't the first to do an approximation. The approximation for small p, large n in the binomial had been done long before Poisson. But I like that picture of Poisson. He looks very nice. Other people, Ernst Abbe in Germany worked for the Zeiss company, and William Gossett in Ireland, who worked for the Guinness Brewing Company, both computed the distribution of cells on a microscopic slide. And that was something that they needed for their work. There's Abbe and there's Gossett. Gossett is known in statistical context as student because he wasn't being an employee of Guinness. He wasn't allowed to do nasty things like publish in the scientific literature that would reflect badly on the company. So he called himself student, and that worked. And he invented student's tea and other things. Other people who came up with stuff, Erlang in 1909 looked at incoming and outgoing telephone calls to an exchange. He worked for the Danish telephone company. And Bateman in 1914 helped some physicists to figure out alpha decay, the distribution of alpha decay over time. So there's Erlang and there's Bateman. Bateman then went to the United States and became a professor of mathematics. But this point, I believe he still was in England. He was working for Rutherford and Geiger. And you might have heard about the Rutherford-Geiger experiment. Here it is. Here's the instrument. They're looking in. The light wouldn't be on when they did this. They would look into this tube, and then they would have a material, some radioactive material, that would give off alpha particles. And in darkness, you would see them as little flashes. Now, anybody who's lying awake at night in the dark know that little flashes you see all the time. But here the flashes were actually due to the particular radioactive material they put in. Bateman figured out that the distribution over time should be Poisson, and that the independent from disjoint time intervals. So that's some of the reinventions of the Poisson process. Now, mathematically, neither of these actually, well, Bateman sort of wrote down a proper thing for the Poisson process, but he wasn't first to do that. The first to do that was a Swedish name called Philip Lundberg, who wrote a thesis in Uppsala on insurance. And the insurance industry realized that this was a terribly important work for them, but they couldn't understand a word of it. So they hired a smart young mathematician named Harald Kramer, who later wrote a book called Mathematical Methods of Statistics that some of you might have encountered, and to explain to them what this meant. And it later turned into the chair in insurance mathematics and statistics at the University of Stockholm. Still exists, and I don't remember who has it right now. So he was looking at the insurance claims. A claim of a certain size, AI, had probability in an interval of very short length, dt, proportional to the length of the interval. And the constant of proportionality was pi. If you set all the AI equal to the same amount, then you get a probability mass function of total claims will satisfy this. That always happens to me when I try to use this. Will satisfy this equation, which is a differential difference equation, which is really the forward equation for the Poisson process. Forward equations were invented some 25 or so years later by Kolmogorov. Anyway, so here's actually the first real derivation of the Poisson process. And you can use this method of thinking of what happens in a small time interval on a lot of other processes. In the case of a general AI, he gets a compound Poisson process, which is the only time I'm going to mention compound Poisson processes. Let's go now to continuous time Markov chains. So Lundberg's equation was rediscovered by a Scottish military physician called McKendrick, Anderson McKendrick. He was working with the British Army in India, and then he was heading the Pasteur laboratory in Pakistan. I bet none of you knew that there was a Pasteur laboratory in Pakistan. I certainly didn't. And then he got injured in Pakistan and was unenlisted and came back to Scotland, where he was the laboratory director of the Royal College of Physicians in Edinburgh till his death. So one of the things he thought about was how white blood cells get rid of bacteria. So leukocytes are one particular kind of white blood cells. And they destroy bacteria, and it has to do with how many things there are in the solution and how fast they can ingest things. He generalized this thing to a birth process, so the distribution of destroyed bacteria is a Poisson process if there's enough leukocytes. Generalized to a birth process that he applied to chemical reactions and a simple epidemic model. All of this in 1914. Let's see if we have a picture of him. There he is. A little late. There wasn't a 1914 picture of him. This is the only one I could get hold of. I usually try to get pictures from about when the people were inventing whatever we're talking about, but it's not always possible. Okay. Now here are some other people. Adney Yule was famous for writing a statistics text that came out in 20 editions and sold more and more for every new edition. But he also invented a model for how species are generated within genera. And that was a birth process again. The more genera you have, the more species you will tend to get. And Wendell Furry was an American physicist who modeled cosmic rays, incidentally by exactly the same model as McKendrick had come up with for chemical equations and Yule had come up with for development of species. Wendell Furry was a pretty radical man and was pulled in front of the House Committee for Un-American Activities several times, but his university refused to fire him, even though he was a suspicious character. Okay. Next chapter, point processes based on Poisson processes. So the most common one is probably a cluster process. A cluster process starts with some primary points, they're here, and then some secondary points that are derived, that are sort of somewhere around the primary points. Sometimes we can connect them so we know which secondary points belong to a particular primary point. Sometimes we don't observe the primary points. We have to deduce where they are, and so on and so forth. It's a very practical process. It deals with things that behave like the Pleiades, clustered things. And Jerzy Neyman, who happened to be my master's thesis advisor, he didn't like my results and didn't take me out for beer for 3 years after I finished my thesis, but it's okay. Then he forgot about it and took me out for beer. He modeled potato beetle larvae. So potato beetle, you have an egg mass that's laid by a mature beetle, and then larvae come out and start moving, and they eat up the potato plant leaves and are very destructive. So it was an important thing for an agricultural statistician, which is what Neyman had been in Poland, to study. And he developed a model that we now called a Neyman-Scott model, because he later used the same model to model clusters of galaxies. And their model doesn't necessarily have Poisson cluster centers. That is, the process of centers does not have to be a Poisson process. It can be a cluster process, for example. And it's called a second-order cluster process. It's a fairly flexible model, and it's been applied to a lot of different things. Name and assume that the dispersions, how far the secondary points got from the primary points, was independent and identically distributed, because that made the mathematics easier. And it's often a reasonable thing. If you think of larvae, they move relatively independently. They don't interact with each other very much. Here's Jerzy Neyman about the time when he invented the potato beetle model. And here's Elizabeth Scott about when they wrote their paper on clusters of galaxies. So Elizabeth Scott was an astronomer. She decided to try to get a master's in statistics, and statistics was led by Jerzy Neyman. And they started writing papers together, and they started living together. Neyman was married, but that didn't bother anybody, including his wife. They died not very long after each other. I was privileged to have encountered both of them in graduate school. Doubly stochastic processes is another thing that is based on a Poisson process. You start with the Poisson process, and then it would have some kind of rate. It depends on time. And now you let that rate be a random variable, or a stochastic process. It has to be a positive stochastic process in order to work, but that's okay. One of the things one can use it for is to describe shot noise. I bet nobody here has encountered shot noise, because you encountered it in vacuum tubes in old radios. But if any of you have worked with old radios, you would have encountered shot noise. And you can write that as an integral with respect to a Poisson process. So it's a sort of a self-exciting process. If there happens to be a lot of noise, there will tend to be more noise, unless the kernel function is decreasing. Campbell in 1909, the short noise was discovered and described by Walter Schütte in 1919, I believe, and 10 years earlier, Campbell came up with a way of computing integrals with respect to these things. The log Gaussian doubly stochastic process is today probably the most common point process model, and basically it's sort of gotten to the stage where you sort of say, have model, will travel. I have a hammer. I can hit every problem with my hammer. I don't like log Gaussian Cox processes because they're not based on any scientific problem that I know of. But Nancy and I have disagreed about that, and we're still friends. The Gauss-Poisson process is one of the few Markovian processes that you can actually work out the distribution for. It is never used. Here's Lucien Lecomte. Lecomte is best known for his asymptotic theory. He was a master of asymptotics. But his work started modeling precipitation, and he's been very influential in the hydrology literature from some papers that are actually quite hard to read, but contain a lot of material. Later in his life, his daughter got cancer, and he started studying cancer and did a lot of work on that. Markovian point processes. Yeah, so I mentioned the Gauss-Markov process. You have to define what you mean by Markovian. Typically, what we mean by Markovian in time is that given where you are right now, the future and the past are independent. So how you got to where you are doesn't matter. It only matters where you are. Now, to do that for things in space, Lévy came up with something he called the sharp Markov property. So you have a set. You look at events outside that set and inside that set. And then given the values on the boundary, you assume that those are independent. So it's very similar in spirit to what I just said in time. Turns out that what he defined by that was exactly the class of doubly stochastic Poisson processes. Well, not quite. What is true is that all spatial processes with the sharp Markov property are doubly stochastic Poisson processes. So it really didn't go anywhere. And somebody else then started thinking about it. So here's Paul Lévy. We'll get back to Paul Lévy if I remember. So the Ripley-Kelly approach does something very similar. They start from the characterization of Gibbs measures by Hammersley and Clifford, one of the very famous unpublished results. And other people have published it, but Hammersley and Clifford never published it because they wanted to get rid of a condition that you can't get rid of. And they had a grad student who came up with a counterexample, and they got fed up with the whole thing and didn't publish it. So you look at a pattern of points in S, in the set S, and then Y is going to be the pattern in the whole space minus X, so everything else. And then you decide that the distribution of the union of those patterns divided by the distribution of the inside pattern, the pattern in S, depends on Y only through the neighbors of X. So it only depends on the nearest neighbors in some sense that you have to define, and it's kind of tricky. You have to define what you mean by a neighbor. You might do it by distance. You can do it all sorts of different ways. And then that turns out to be a product of interaction functions where phi is 1 unless all the points in the set Y or the pattern Y are neighbors. So it depends on what you mean by neighbor, whether what that structure looks like. Here's Brian Ripley, here's Frank Kelly, and now we get into people who are so modern that they have color pictures of them. And this has led to a large class of processes that are only there because we can write this down. We can model them by writing down the interaction function. Let's see if I have time for some terminology. Oh, yeah. Point pattern was first used by Eggenberger and Poya in a paper in 1923 that introduced what we now call contiguous distributions. Poisson process is interesting. I know where the first papers are. It's the thesis by Lundberg, different Lundberg from the one we had before, not related, but another Swedish graduate students, this time in Stockholm, and Will Feller. They both had a paper Lundberg had a thesis in 1940. Feller had a paper in 1940, so it was presumably written in 1939. Nobody before that had used the term Poisson process. They called it all sorts of, they called it the elementary process, they called it Poisson noise, but nobody had used the term the Poisson process. So my theory, since they both were at the University of Stockholm, and they both interact at the time, in 1940, Feller had left for the US, but in 1939 he was still in Stockholm where he fled from Poland. My theory is that they were just talking in the corridors and deciding that they needed a name for this thing that they all were using for different reasons. And so they decided to call it Poisson Process. The word then spread by Feller giving a talk at the first Berkeley Symposium of Mathematical Statistics and Probability, which was the first major statistics conference after World War II. And there he used the term Poisson Process, and I think it just, everybody said, well, it's good to have a name for that. But again, this is guesswork, but it sounds like a likely explanation to me. There are other things that they came up with there. In Stockholm, they also came up with the word point process, and that was a thesis by Victor Palm, telecommunications engineer, in 1943, and he uses that term. I have not been able to find it anywhere earlier. But, finding the first instance of anything is something that's very easy to falsify. All you need to do is find it. So if you do, let me know. I collect these things. W stochastic Poisson process was named by Bartlett in 1963, but was invented by Cox in the early 50s, and the Cox process was called the Cox process. The Cox process is the same thing as the W stochastic Poisson process. Remember, W stochastic Poisson process was invented by Lacombe, and so therefore it's called the Cox process. Krickeberg in 1972 came up with that name. Okay, discrete-time Markov chains. Let's see how we're doing on time. Oh, we still have 15 minutes. Good. Discrete-time Markov chains. Quetelet was a Belgian statistician. He was the first person who thought of the normal distribution as a distribution of data, not the distribution of errors. Everybody else had thought of it as a distribution of errors of measurement and things like that, typically in astronomy again. But he thought of it as a distribution of data, and he tried to describe everything under the sun as a normal distribution, sometimes more successfully than other times. And this particular paper dealt with precipitation. He was also the director of meteorology in Belgium, and so he cared about predicting rainfall. And so he had a testing approach that he was going to use to distinguish independent data from something else. He didn't believe that independence was really the right assumption, so essentially what he did is developed a test of independence, where the alternative again is a much later word, it came up in the mid-30s by Neyman and Pearson, but the alternative was this thing that depended on where you had just been. So if it rains today, it's more likely to rain tomorrow. That's a very good model for rainfall in Seattle, where I live, as Nancy knows. So there's Quetelet. He also formed international statistics organizations and things like that, was very active in making statistics a subject. Markov actually came up with the name chain. I haven't figured out who first called it the Markov chain, but Markov came up with the word chain. But he did it, he wanted it as a counterexample to what he had misread Nebrakov to call a necessary condition for the law of large numbers. And it worked as a counterexample to that, and then he later applied it to some data just because he liked doing things that upset mathematicians. He also liked to do things that upset the government. He refused to take money from the academy, the Russian academy. because they would only give him enough money for a pair of shoes, and he wanted more money than that. And he also didn't like the fact that they'd given a prize to the Tsar, and so he was seen as a revolutionary, at least by the Tsar. So here's Markov around the time of 1906, I think, although the portrait is a couple of years later. Okay, Brownian motion. So let me see if I can get this to show. So this is a movie of Brownian motion. If you look really carefully, you see that there's stuff going on. Now it stopped. Okay, so this was a picture of tobacco smoke. So remember the tobacco smoke that was supposed to... It doesn't go anywhere. It doesn't move very far from where it is. We can do another picture that's a little easier to look at, perhaps. Where is it now? Why doesn't it show up? There we are. So here we have one big particle that's being bombarded by all these small particles. So this is the kinetic theory in action. Remember, we are now, well, Brown discovered this motion in the mid-1800s. And he thought maybe it was the molecule of life. Maybe this was how life worked. He had actually pollen in a container with a liquid, and the pollen kept moving around like that yellow thing there does. Here's Brown. He did lots of experiments. He worked with fossilized plants. Same thing came up there, and so that still sort of helped with molecule of life idea. Then he did it for sand from the pyramids in Egypt, which had no life associated with it within any reasonable sense of the word. And it did the same thing for that. You put sand in a container of liquid, and it starts moving around, especially if you heat it up. The motion never stopped. You had a sealed test tube with this motion going on, and 20 years later, it was still going on. And that was really weird. And everybody agreed, and nobody had an idea what was going on. So it seemed to violate the second law of thermodynamics. It seemed to be a perpetual motion. And if it is, we can use it as a perpetual motion machine, and so on and so forth. Of course, we can't. It's just that second law of thermodynamics operates on very large averages. Léon Gouy redid Brown's experiments and suggested that kinetic theory could actually explain why it was moving and why it kept moving as long as you kept the thing at a constant temperature so that the molecules would be moving around. And he published that in a chemistry journal, and in the same journal there was another article saying that this kinetic theory of heat is totally ridiculous because you'll never be able to observe an atom. But it would take 20 more years, and somebody would observe it. So the Brownian motion process was first modeled by an economics student in Paris called Louis Bachelier. Wrote the dissertation which defined the Brownian motion process as we know it. Here's Louis Bachelier a little bit before he did that. He's about 15 years old there. That's the only picture I could find of him. But he was 30 when he did that, so just multiply him by 2. So what he did, he applied the heat equation to diffusional probability. Poincaré was very impressed. He was on the committee. He was very impressed by that and thought it would have been really good if he'd gone a couple of steps further invented stochastic differential equations, which he nearly did, but not quite. But Bachelier was the first person to prove the Chapman-Kolmogorov equation. Again, Chapman and Kolmogorov are much later in time and did not come up with it. The most famous person to model the actual Brownian motion, of course, was somebody else. I didn't tell you what Bachelier was modeling. He was modeling stock prices. Einstein, yeah, the usual Einstein. He also invented fast Fourier transforms and a few things like that. Sorry, discrete Fourier transform, not fast. Realized that observations were not of the motion of a particle. They were of the net displacement of the particle over a period of time. And that was so you essentially had a discrete time approximation. That was a very important finding because people had tried to measure the velocity of these particles, and they couldn't. You know, you take change in distance divided by change in time, and it didn't converge. And of course, we know that the Brownian motion process has no derivatives. So this displacement from the bounces, the fact that it's moving, generates some energy. And there has to be a counterpart. This doesn't work again. And that's osmotic pressure. And then you just set those two forces equal. And there's Van Hoff's law that describes osmotic pressure. And you just figure it all out, and you compute the diffusion coefficient, which you then can measure at the fixed point in the volume, as a function of Avogadro's number. But of course, he didn't know Avogadro's number. So that wasn't discovered yet. So what he said, it is possible that the movements to be discussed here are identical with the so-called Brownian molecular motion. However, the information available to me regarding the latter is so lacking in precision that I can form no judgment in this matter. Here's Einstein in 1905, when he also happened to write two more papers. One was on Brownian motion, and he wrote a paper on special relativity. And then he wrote a third paper, which he got a Nobel Prize for. Nobody remembers what it is except physicists. Which means I've forgotten. Okay, so still, people did not generally believe in the thermal theory, in the kinetic theory of heat. But people started doing experiment, and Perrin actually managed to observe atoms, and in 1926 he got the Nobel Prize in Physics for determining Avogadro's number, and I actually have used data from 1916 to get a confidence interval for Avogadro's number, which is kind of neat. And that brings us to the end. Thank you.